Welcome back. Last episode, we computed areas of flat regions between two curves. Today, we go one dimension up, take that region, spin it around an axis, and ask for the volume of the 3D solid it sweeps out. These are called solids of revolution, and they have three classical methods of computation: disks, washers, and shells. The names sound different, but they're three flavors of the same idea. Slice the solid into thin pieces whose volume you can write down, then integrate. The disk method, slice perpendicular to the axis, each slice is a circular disk, volume is pi r squared times thickness. Integrate. The washer method, same, but the region had a hole, so each slice is a washer, an annulus. The shell method, slice parallel to the axis instead, each slice is a thin cylindrical shell, volume is circumference times height times thickness. Three methods, one structural idea. Three worked examples will lock it in: 8 pi, 2 pi over 15, and 8 pi again. We'll also touch the history, Cavalieri, Kepler, and the slicing argument that predates calculus by decades. Let's go. First, what exactly is a solid of revolution? Take a region in the plane, like the region under a curve, or the region between two curves. Pick an axis of rotation, usually the x-axis or the y-axis. Now rotate the region a full 360 degrees around that axis. The 3D shape you sweep out is called a solid of revolution. You already know lots of examples. Spin a half disk around its flat edge, you get a sphere. Spin a right triangle around one of its legs, you get a cone. Spin a rectangle around one of its sides, you get a cylinder. Spin a small circle around an axis it doesn't touch, you get a torus, a donut. Today's bread and butter is the region under a curve y equals f of x on an interval from a to b, rotated around the x-axis. The resulting solid is symmetric about the x-axis. Every perpendicular cross-section is a circle, because that's what rotation produces. The radius of that circle at position x is exactly f of x. That's the key geometric fact. Cross-section perpendicular to the axis of rotation is a circle of radius, f of x, area pi times f of x squared. That's the whole disk method, sitting right there waiting to be integrated. The disk method, formally. We have a region under y equals f of x on the interval from a to b, with f greater than or equal to 0, rotated about the x-axis. Slice the resulting solid with planes perpendicular to the x-axis. Each slice is a thin disk. Look at the slice at position x. Its radius is f of x, because the topmost point of the original region at that x-coordinate sits at height f of x, and when rotated, sweeps a circle of that radius. The disk's area is pi r squared, which is pi times f of x squared. Its thickness, as we take it infinitely thin, is dx. So its infinitesimal volume is pi times f of x squared dx. Sum all the disks by integrating from a to b, v equals the integral from a to b of pi times f of x squared dx. That's the disk method formula. One line. The whole content is, a cross-section is a circle of radius f of x. Notice the structural similarity to last episode. For area between curves, we wrote a equals the integral from a to b of the strip height, dx. For volumes of revolution, we write v equals the integral from a to b of the slice area, dx. Same template, one dimension up, the integrand is the measure of the cross-section, whatever measure means in our dimension. First worked example. Spin the region under y equals the square root of x from x equals 0 to x equals 4 around the x-axis. What volume does it sweep? Picture it. The curve y equals the square root of x starts at the origin and rises to height 2 at x equals 4. The region beneath it is a kind of fingernail shape hugging the x-axis. Spin it around the x-axis. You get a 3D solid shaped like a horn or trumpet bell, flaring from a point at the origin out to a disk of radius 2 at x equals 4. This is a paraboloid of revolution. Disk formula. V equals the integral from 0 to 4 of pi times f of x squared dx, with f of x equals the square root of x, so f of x squared equals x. The integral becomes v equals pi times the integral from 0 to 4 of x dx. Antiderivative of x is x squared over 2. Evaluate from 0 to 4, 16 over 2 minus 0, which is 8. Multiply by pi, the volume is 8 pi. Sanity check. The solid sits inside the cylinder of radius 2 and length 4. That cylinder has volume pi r squared h, which is pi times 4 equals 16 pi. Our paraboloid is exactly half that, 8 pi. That ratio, paraboloid of revolution is half its bounding cylinder, is a classical result going back to Archimedes. He proved it in the 3rd century BC without calculus. We just rederived it in 2 lines. Here's the picture. The curve y equals f of x in solid blue, with its mirror image y equals negative f of x in dashed blue below the axis. That's where the rotated solid extends to. Pick a representative slice at some position x. I've drawn it as a vertical red ellipse, which is what a circular disk looks like when you view it slightly edge-on. The disk's radius is f of x, labeled vertically on the right edge. The disk's thickness is the tiny dx, labeled at the bottom. The volume of this thin disk is its area, pi times f of x squared, times its thickness dx. Integrating from A to B stacks up all the disks and gives the volume of the solid. That's the whole disk method in one picture. The slice perpendicular to the axis of rotation is a circle, the radius of the circle is the function value, and the integrand is the area of that circle. Next, the washer method. This is for regions with holes. Suppose your region in the plane is bounded above by f of x and below by g of x, with f greater than or equal to, g greater than or equal to 0. When you rotate this region around the x-axis, the upper curve sweeps an outer surface, and the lower curve sweeps an inner surface, and the solid has a hollow core. Slice the solid with a plane perpendicular to the x-axis. The cross-section is no longer a solid disk, it's a washer, also called an annulus, a flat ring. Outer radius f of x, inner radius g of x. Its area is the area of the outer disk minus the area of the inner disk, pi times f of x squared minus pi times g of x squared. Multiply by thickness dx, integrate from a to b, the volume is the integral from a to b of pi times the quantity f of x squared minus g of x squared dx. The most common student mistake here, writing pi times the quantity f minus g squared instead of pi times the quantity f squared minus g squared. Those are very different. The cross-section is a ring, not a disk with side length f minus g. You compute the area of the outer disk, subtract the area of the inner disk. Square first, then subtract. The washer method is just the disk method with a hole, but that's square first, then subtract. Bookkeeping trips everyone up. Watch the algebra. Worked example 2, the washer method. We'll take the same region from last episode, the region between the line y equals x and the parabola y equals x squared on the interval from 0 to 1. Last time we computed its area as 1/6. This time, we spin it around the x-axis and ask for the volume of the resulting solid. The picture, the line is on top, the parabola is on bottom. Spinning, the line sweeps the outer surface, a cone actually, and the parabola sweeps the inner surface, a paraboloid. The solid between them is a cone with a paraboloid bored out of it. At position x in the interval from 0 to 1, the cross-section is a washer. Outer radius f of x equals x, so f of x squared equals x squared. Inner radius g of x equals x squared. So g of x squared equals x squared squared, which is x to the fourth. The washer's area is pi times the quantity x squared minus x to the fourth. Setup, v equals pi times the integral from 0 to 1 of the quantity x squared minus x to the fourth dx. Antiderivative of x squared is x cubed over 3. Antiderivative of x to the fourth is x to the fifth over 5. So we get pi times the quantity x cubed over 3 minus x to the fifth over 5, evaluated from 0 to 1. At 1, 1/3 minus 1/5 equals 5/15 minus 3/15 equals 2/15. At 0, 0, subtract, the volume is 2 pi over 15. Same region as last episode, with area 1/6, spun around the x-axis. Its volume is 2 pi over 15. Two different geometric measures of the same starting region, and calculus gave us both with the same template. Now the third method, shells. This one is the most beautiful and the most underrated. Same kind of solid, but now we slice differently. Take the region under y equals f of x on the interval from a to b with a greater than or equal to 0, and rotate about the y-axis this time, not the x-axis. Instead of slicing the solid perpendicular to the axis of rotation, which would give weird-shaped cross-sections, slice it parallel to the axis. Take a thin vertical strip in the original 2D region at position x with dx, running from y equals 0 up to y equals f of x. When we rotate this strip around the y-axis, it sweeps out a thin cylindrical shell, a tube of radius x, height f of x, and thickness dx. What's the volume of a thin cylindrical shell? Imagine slitting it lengthwise and unrolling it into a flat sheet. The sheet has width equal to the circumference 2 pi x, height f of x, and thickness dx. Its volume is the product, 2 pi x times f of x times dx. Sum all the shells by integrating from a to b. V equals the integral from a to b of 2 pi x times f of x dx. That's the shell formula. Same solid, sliced into cylindrical layers instead of disks, like the layers of an onion expanding outward from the axis. Quick aside, why two methods? Why not just always use disks? Because sometimes the disk method forces a painful change of variables, and shells let you avoid it. Concretely, if you rotate around the y-axis and use the disk method, your cross-sections are perpendicular to the y-axis. They're disks of radius x at height y. But to integrate over y, you need to write the radius as a function of y, which means inverting y equals f of x into x equals f inverse of y. If f doesn't have a clean inverse, you're in trouble. The shell method dodges this. Rotating about the y-axis, shells let you keep the variable as x. Your strips are at x of height, f of x, and you integrate dx from a to b. The function f stays in its given form. Symmetrically, if you rotate about the x-axis, disks are natural, cross-sections perpendicular to the x-axis, and shells require inverting. Rule of thumb, slice perpendicular to the axis of rotation, you get disks or washers. Slice parallel to the axis, you get shells. Pick whichever method lets you keep your given function in its given form, without inverting. Or, equivalently, pick the method whose slicing direction matches the variable your function is given in. Third worked example, the shell method. Rotate the region under y equals x squared from x equals 0 to x equals 2 around the y-axis. Picture it. The parabola y equals x squared rises from the origin to height 4 at x equals 2. The region beneath it sits in the first quadrant, bordered on the left by the y-axis. Spin it around the y-axis. You get a 3D solid that looks like a bowl, a paraboloid-shaped bowl with an inside. Actually, you get a paraboloid-shaped bowl with the inside also filled in, since the region includes everything below the curve down to the x-axis. Apply the shell formula. V equals the integral from 0 to 2 of 2 pi x times f of x dx with f of x equals x squared. The integrand is 2 pi x times x squared, which is 2 pi x cubed. The integral is 2 pi times the integral from 0 to 2 of x cubed dx. Antiderivative of x cubed is x to the 4th over 4. Evaluate from 0 to 2, 16 over 4 minus 0, which is 4. Multiply by 2 pi, v equals 8 pi. Volume is 8 pi. Same numerical answer as the first example, y equals the square root of x on the interval from 0 to 4 rotated about the x-axis. That's a coincidence. Different solids, different methods, but a cute one. The disk method and the shell method both happen to give 8 pi here. Notice how clean the shell calculation is. If we try to use disks on this same problem, we need to write x equals the square root of y and integrate pi times the square root of y squared dy from 0 to 4, then also subtract off the inner radius issue. Shells just handle it directly with the function as given. Here's the shell picture, side by side. On the left, the 3D solid swept out by rotating y equals x squared around the y-axis. You see the parabolic outline, the top cap as an ellipse at y equals 4, and one representative cylindrical shell highlighted in red at radius x equals 1.2. Its radius is the horizontal distance from the axis. Its height is f of x equals x squared equals 1.44 at this position. Its thickness, infinitesimally, is dx. On the right, the same shell, slit lengthwise and unrolled flat. It becomes a thin rectangular sheet. The width of the sheet is the circumference of the shell, 2 pi x. The height of the sheet is the height of the shell, f of x. The thickness of the sheet is dx, so the volume of the shell is 2 pi x times f of x times dx, a thin rectangular slab. Integrate this from x equals a to x equals b, and you've summed all the cylindrical layers, from the inner one near the axis to the outer one at the edge. That's the shell method in one picture. The unrolling argument is the heart of it. You're converting a curved cylindrical layer into a flat sheet whose dimensions you can read off. A bit of history, because this stuff is genuinely older than calculus and worth knowing where it came from. Johannes Kepler, 1615. The same Kepler who gave us planetary laws also wrote a book called Nova Stereometria Doliorum Venariorum, New Solid Geometry of Wine Casks. He wanted to compute the volume of wine barrels accurately because Austrian wine merchants were using bad formulas and getting cheated. He worked out volumes by slicing the barrels into thin disks, essentially the disk method, but without the integral symbol. He summed approximations and took limits informally. Bonaventura Cavalieri, 1635, published Geometria Indivisibilibus, Geometry of Indivisibles. He stated what we now call Cavalieri's principle. If you slice two solids with parallel planes, and every corresponding pair of cross-sections has the same area, then the two solids have the same volume. This principle alone, with no calculus, gives you things like the volume of a sphere, by comparing it to a cylinder with cones removed. Cavalieri's principle is exactly the conceptual content of the disk method. Cross-sections determine volume. The integral symbol, the integral of a of x dx that Newton and Leibniz introduced in the next generation, just made the summing. The slice's argument rigorous and automatic. So when we write the integral from a to b of pi times f of x squared dx, we are using a notation that's 400 years old in idea and 350 years old in symbol. The idea was there before the machinery. Zoom out. The disk, washer, and shell formulas are three instances of one master template. V equals the integral from a to b of a of x dx, where a of x is the area of the cross-section at position x. For disks, the cross-section is a circle of radius f of x, so a of x equals pi times f of x squared. For washers, the cross-section is an annulus, so a of x equals pi times the quantity f squared minus g squared. For shells, the geometry is slightly different. We're slicing parallel to the axis and getting cylindrical layers, not flat slabs. But the volume of a thin cylindrical layer is a lateral surface area times thickness, which fits the same measure of the slice times dx template. And the template extends beyond rotational solids. Suppose you have a solid that isn't a solid of revolution at all. Maybe its cross-sections at position x are squares of side s of x. Then a of x equals s of x squared and v equals the integral from a to b of s of x squared dx. Maybe the cross-sections are equilateral triangles of side t of x. Then a of x equals the square root of 3 over 4 times t of x squared. Maybe semicircles. Whatever shape, you write down its area as a function of x and integrate. The disk and washer methods are just the most common case. Cross-sections happen to be circles or annuli because the solid is rotational. But the underlying idea, volume is the integral of cross-sectional area, is the real content. That idea is essentially Cavalieri's principle, and it's the whole game. 5 pitfalls, since this topic invites errors at every step. 1. Washer integrand is pi times the quantity f squared minus g squared, not pi times the quantity f minus g squared. Difference of squares, not square of difference. Sketch the annular cross-section if you're unsure. Outer disk area pi f squared, inner disk area pi g squared, washer area is the difference. 2. Wrong method for the axis. If you're rotating about the y-axis and your function is y equals f of x, the shell method is almost always cleaner than the disk method. If you're rotating about the x-axis and your function is y equals f of x, disks are cleaner. The wrong choice forces you to invert the function, often with square roots. 3. Off-axis rotation. If you're rotating about a horizontal line, y equals c, that isn't the x-axis, the radius of each disk is the distance from the curve to that line, f of x minus c. Many students just write f of x out of habit. Sketch the picture so you can see the radius. 4. Forgetting the 2 pi in the shell formula. The shell circumference is 2 pi x, not just x. Forgetting the 2 pi is a 6-fold error. 5. Forgetting the pi in the disk formula. Disk area is pi r squared, not r squared. The pi pulls outside the integral. Easy to drop in the rush. The universal preventive, sketch the solid. A rough 3D sketch tells you the axis, the slice shape, the radius, and which method to use. 2 minutes of sketching saves an entire wrong answer. Recap. Solid of revolution, rotate a 2D region around an axis to produce a 3D solid. Volume by slicing. Disk method. Region under y equals f of x on the interval from a to b, rotated about the x-axis. Cross-sections perpendicular to the axis are disks of radius f of x. Volume is the integral from a to b of pi times f of x squared dx. Worked example, y equals the square root of x on the interval from 0 to 4, rotated, gives 8 pi. Washer method. Region between y equals f of x on top and y equals g of x on bottom, rotated. Cross-sections are washers, annuli, with outer radius f and inner radius g. Volume is the integral from a to b of pi times the quantity f squared minus g squared dx. Worked example, between y equals x and y equals x squared, rotated about the x-axis, gives 2 pi over 15. Shell method. Region under y equals f of x on the interval from a to b with a greater than or equal to 0, rotated about the y-axis. Slice parallel to the axis into thin cylindrical shells. Unrolling gives circumference times height times thickness. Volume is the integral from a to b of 2 pi x times f of x dx. Worked example, y equals x squared on the interval from 0 to 2, rotated about the y-axis, gives 8 pi. Master template, the one that unifies all three, v equals the integral from a to b of a of x dx, where a of x is the area of the cross-section at position x. This is Cavalieri's principle, 400 years old, formalized by Newton and Leibniz with the integral. Next episode, arc length and surface area. Instead of asking for the volume swept by a region, we'll ask for the length of the bounding curve and the area of the surface it sweeps. Same Riemann template, one more flavor of geometric measure. See you there. That's volumes by disks, washers, and shells. If this helped, hit like, drop a comment, and consider subscribing. It's the single most useful thing for the channel. Post your favorite solid of revolution below. Tell me what region you spun, around what axis, and what volume you got. Bonus points for tidy multiples of pi. Next episode, arc length and surface area. We'll stop asking what 3D solid the curve sweeps out and start asking how long the curve itself is, and how much surface area it sweeps when rotated. Same Riemann recipe, 2 more geometric quantities. See you there. Volumes of solids of revolution are where calculus earned its keep as the language of 3D geometry. We computed 3 volumes today, 8 pi, 2 pi 15, and 8 pi, by writing down the cross-sectional measure at position x and integrating. Disks, washers, and shells are 3 flavors of the same template, measure of the slice times the infinitesimal thickness integrated. Same template as area between curves. Same template as the original Riemann sum. The only thing that changes is what measure of the slice means geometrically. Next episode, we close the cycle. Instead of asking for the volume the curve sweeps out, we'll ask for the length of the curve itself, and the area of the 2D surface it sweeps when rotated. Arc length and surface area, same Riemann recipe, one more geometric quantity to measure. Subscribe so you don't miss it. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.